As the global industry becomes more power-hungry, scientists are working around the clock to tap into new energy sources. Most of us are familiar with nuclear power, which is a reliable source of energy. But a breakthrough in nuclear energy research promises to change everything in the power sector. The groundbreaking achievement is in nuclear fusion, and industry experts are going crazy with excitement because of it. Which company made this discovery? How does nuclear fusion work? And how is it different from nuclear fission that we have used for centuries? Nuclear power has come a long way since the first nuclear plant connected to an external plant went operational. That was in Obninsk in Russia in 1954, and it added 5 megawatts of electricity to the power grid. The city would go on to have the identity of a nuclear city with at least 12 scientific research institutions and a technical university, most of them focused on nuclear power engineering, nuclear physics, radiation technology, and the likes. As of last month, Statista reported there were 439 nuclear reactors in operation globally, situated in about 30 countries. The US has the most reactors, hosting at least 92 units. The largest reactors under construction as of May 2022 were located in the UK, and they have a gross electricity generation capacity of 1,720 megawatts. However, the country with the highest capacity of nuclear reactors under construction worldwide was China, where reactors with a total of 15 gigawatts were being fabricated at the time. Nuclear power has many benefits, but there are disadvantages too, which is why intense research is going on in the field. All existing nuclear reactors are based on nuclear fission, but scientists have been pursuing another method of producing nuclear energy, nuclear fusion. Recently, a group of researchers in the UK have recorded a breakthrough in nuclear fusion that opens up many exciting possibilities in energy production. The researchers are attached to the Joint European Torus, or JET laboratory near Oxford in central England. What is amazing is that they have managed to duplicate the process stars use to generate heat. But more importantly, this discovery has been hailed as an important milestone in the global effort to get more of our energy from clean sources. But how is nuclear fission different from nuclear fusion? To understand the difference, we will quickly look at how nuclear fission works. Every nuclear power plant has at least one reactor, and its job is to house and control the nuclear fission process. In this step, a neutron is made to collide with a uranium atom, which splits it. This will release a large amount of energy in the form of heat and radiation. Interestingly, as the uranium atoms split, more neutrons are also released. These neutrons continue to collide with other uranium atoms, and the process repeats itself over and over again. This process is called a nuclear chain reaction. The reaction is controlled inside the reactors to produce a desired amount of heat. The most common nuclear plant fuel is uranium, which is the most widely used by nuclear plants for nuclear fission. Uranium is a non-renewable energy source. You commonly find it in rocks worldwide. Nuclear power plants use a particular kind of uranium called U-235 for fuel because its atoms are easily split apart. Although uranium is about 100 times more common than silver, U-235 is relatively rare. What about nuclear fusion? Like we have said before, this is the process the sun uses to generate heat and light, which reaches us on Earth. In a fusion reaction, two light nuclei come together and form a single heavier nucleus. This merger releases energy because the total mass of the resulting single nucleus is less than the mass of the two original nuclei, so the leftover mass is transformed into energy. Remember Einstein's equation. It says, in part, that mass and energy can be converted into each other, and this is what the fusion process hinges on. What scientists are now trying to do is to find a safe method of harnessing energy from fusion in machines on Earth. Many different elements in the periodic table are suitable for nuclear fusion. However, more research has been focused on a deuterium-tritium or DT fusion reaction. DT fusion produces a neutron and a helium nucleus. It also releases much more energy than most fusion reactions in the process. In a potential future fusion power plant, such as a tokamak or stellarator, neutrons from DT reactions would generate power for our use. Researchers prefer DT reactions both because they produce tremendous energy and they occur at lower temperatures than other elements. Using nuclear fusion, the researchers have been able to generate sustained energy, and the amount of energy is more than double the earlier record. According to the UK Atomic Energy Authority, this result is the clearest demonstration worldwide of the potential for fusion energy to deliver safe and sustainable low-carbon energy. The UK's Science Minister George Freeman is also full of praise for the team because he can see the massive potential in their achievement in clean and safe energy generation. The breakthrough came after decades of tests and refinements at the Culham Centre for Fusion Energy, where the JET experiment was carried out. The lab uses a tokamak for its studies. The JET happens to be the largest and most powerful operational tokamak machine in the world. Inside, a tiny amount of fuel made up of deuterium and tritium is heated to temperatures 10 times hotter than the center of the sun to create plasma. Both are isotopes of hydrogen, and you may hear deuterium sometimes called heavy hydrogen. This is held in place using superconductor electromagnets as it spins around, fuses, and releases tremendous energy as heat. Since both nuclear fission and fusion produce energy, why are these researchers pursuing the latter? There are many benefits actually. To start with, fusion when controlled produces 4 times as much as nuclear fission reactions pound for pound. The energy is nearly 4 million times more energy than a chemical reaction such as the burning of coal, oil, or gas. As such, fusion can provide the kind of baseload energy needed to provide electricity to our cities and industries. Another point in favor of fusion is the fuel. You can get deuterium from water, which is abundant on the planet. As for tritium, you will get it from fusing neutron with lithium. Lithium happens to be available enough to last the next 1,000 years without touching the sea, which can keep us in supply for millions of years. So we are not running out of fuel for nuclear fusion anytime soon. Another advantage has to do with the one that scares lots of people when it comes to nuclear energy: radioactive waste. Authorities have to take special care of the waste products from nuclear power plants that use uranium because they produce harmful radiation. But nuclear fusion reactors produce no high-activity, long-lived nuclear waste. The activation of components in a fusion reactor is low enough for the materials to be recycled or reused within 100 years. Nuclear fusion is also safer because the nuclear meltdown simply can't happen inside a tokamak that is based on nuclear fusion. This is because when any disturbance occurs, the plasma cools in a matter of seconds and the reaction stops. So nuclear fusion will never be responsible for tragedies on the scale of the Chernobyl disaster. Nuclear fusion is also projected to be cheaper, especially as the technology matures and economy of scale comes into play. In addition, fusion doesn't use fissile materials like uranium and plutonium. Radioactive tritium is neither a fissile nor a fissionable material. There are no enriched materials in a fusion reactor like ITER that could be exploited to make nuclear weapons by bad faith actors. Lastly, adding nuclear fusion as an energy source diversifies our energy portfolio. The next step for the JET experiment is scaling up. The researchers have demonstrated the ability to create and sustain fusion for 5 seconds, but of course, we need far longer times for the process to become viable as a conventional power source. In fact, the energy produced here can only boil about 60 kettles of water. Actually, JET couldn't run any longer without damaging the copper electromagnets. It even had to undergo more than 2 years of renovation to prepare the machine for the onslaught. A larger and more advanced version of JET called ITER is currently being built in southern France, where the Oxford data will prove vital when it comes online, possibly as soon as 2025. It is an ambitious $25 billion project that will take nuclear fusion research further than JET managed to do. It is true that nuclear fusion is more complicated, which means lots of issues have to be addressed before it becomes a common source of power. However, these challenges are being worked on by the Eurofusion Consortium, which comprises some 5,000 science and engineering experts from across the EU, Switzerland, and Ukraine. Let's hear what you think of nuclear fusion in the comments section below.